In section 6.5, we will look at linear inequalities. An inequality consists of two or more expressions joined by some inequality symbol. And here are some examples showing the four different inequality symbols. This is 2 is less than 7. Remember that we read these symbols left to right. So the fact that the left side is smaller than the right-hand side, it means that this is the less than symbol. In a similar way, we'll go ahead and look at x is greater than 2. This, of course, is something that's a variable and a number, so we consider the values that make this a true statement, which is where we'll focus on most with the exercises. This one, we have 3x minus 5 is greater than or equal to 10. So again, just recall that this little bar underneath the greater than symbol means that this is also possible for a equal to. So we're going to find the value of x that we could put the value of x. And again, there's more than one that will plug in. That will either leave the left side greater than 10 or equal to 10. And then, of course, if you were to reverse the symbol, we have the less than or equal to part right here. In this last scenario, 4 is less than x is less than or equal to 6. This is a compound inequality, and we have a statement down here below. So we reviewed all the symbols, and again, we want to go ahead and find the solutions on the number line. And that is to say the values that we can go ahead and plug in for x that give us a true statement. So in this case, all of the values that are less than 5. So 4, 3, 2, 1, and so on. And again, whether you include the decimals depends on what type of number, and we'll look at those two scenarios below. So recall that if it is not equal to, you'll use an open circle and then shade to the left. And if it is greater than, it's going to be an open circle, shade to right. And maybe one little caveat about the shading direction, that only works when x is on the left. And then whenever you have the equal to part of the inequality, you'll use a closed circle on the number line. Finally, as stated above, an inequality of this form, where it essentially uses two inequality symbols, is going to be referred to as a compound inequality. And another way we can go ahead and write this right here is we want to consider the two inequalities, namely that 4 is less than x, and the other scenario where x is less than 6. So if you really think about this, 4 must be less than x, so that is another way. If we could also reverse this and say that x is greater than 4 and x is less than 6. So the only numbers are there, the values that make that true are the numbers between 4 and 6, not including 4 and 6. All right, and we'll look into a couple examples down below. So just using this compound equality as an example, we could go ahead and I'm going to go ahead and put some number lines. I already went ahead and put some number lines in the graph, so you may want to go ahead and just pause the video occasionally to draw some nice lines. But the solution set, the values that we can go ahead and plug in for x that make this a true statement, consist of all real numbers. So real numbers include decimals that are greater than 4, which we said right here. The numbers that are greater than 4, and they also have to be less than or equal to 6. So again, maybe just a little bit of an adjustment. There's a little typo in the notes right here. That should technically have an equal to sign right here. So just to be consistent with the wording, we'll go ahead and add that. So we have 4 here, then we have 6 over here, and we'll go ahead and put an open dot above 4 and a closed dot above 6, and then we'll simply shade between them. So right there are the values that are solutions to the compound inequality. And again, we have 5 right here. Well, let's closer to right there in the middle. But notice that the decimal values are still included. All right. So let's go ahead and just do several exercises. And there's a reason I have these. We'll get to that in a moment. But we're going to first focus on the solution set where x is a real number. So it includes decimals, fractions, irrational numbers, so on. So number one, where x is greater than or equal to 4. So again, let's just put 4 on the number line. It's greater, so we're going to be shading to the right. And again, is equal to 4, so we'll put a closed dot right there. So just keep in mind that you could only shade to in the direction that the inequality is pointing if the x is on the left side of the inequality. I'd always encourage you as we go through this just to reason through this. What are the values of x that are greater than or equal to 4? Well, 4, 5, 5.5, so on. In the case of number 2, well, let's go ahead and see x is less than or equal to -2. So let's put a -2 right here. The values that are less than that are to the left, and it's a closed dot because it is an equal to. In the case of number 3, we have a compound inequality. So let's just put a -3 right here. Let's put 2 right here. And again, technically there's like -2, -1, 0, and 1 if you want. But again, it's going to be a closed dot on both the above the -3 and the 2 because we are including those values with the equal to, and then we just shade between them. One other thing I should go ahead and say before we get to the more complicated examples is what if we were to replace the word real with the word integer? Or again, integers are whole numbers, positive or negative. So the way that would change this is, yes, we would still have 4 right here, and we're still going to be looking at the values to the right. Let's zoom in here. So you'll still put a closed dot right here, but integers don't include the decimals. So essentially, the solution set would just be a bunch of points right above the integers. And again, you would continue that pattern to the right. Same principle here. If we had a negative, let's say we have a -2, then we would have -3, we would have -4, and so on. So we'll just do the dots with so on. So you would shade the -2, you would shade the -3, you would shade the -4, and of course you would just continue this pattern to the left. Do not draw the line whenever you're dealing with integers, because integers, like we said, are just whole numbers. And then lastly, let's see, we had -3, -2, -1, 0, 1, and 2. And the integers that satisfy that are just the ones that are whole numbers. So negative or positive or 0. So those are the basic examples. And the rest of the lesson, I'm just going to focus on the real numbers. But again, remember, if you see something where it says integer in your homework, that you just choose, or I think these are multiple choice on the homework. So just choose the one that have the points and not the actual line. So like so. These are the ones we're focused more on because we'll deal with these more if for linear inequalities if we were to go that far. Okay, so a couple other things to keep in mind. Let's just look at number 4. So just like you could solve linear equations, you can solve linear inequalities. So you have to solve this for x. So what I'm going to do is I'm going to subtract 2 from both sides of the linear equality. So here x is less than 2, and now that we're in this form, we can just put a 2 right here, open dot, and then we'll just be shading to the left. So there is the answer to 4. In the case of number 5, we have a fraction. So again, you have ideas wherever we can think of this. We're dividing by 3, so what we need to do is we need to multiply both sides by 3. You could also think of it as cross multiplication if you want to, but 3's cancel here, so negative x is greater than or equal to 9. And then we divide by a -1, or multiply both sides by -1, however you want to think about it. So x and -9, but what we do need to remember is to flip the inequality whenever we divide by a negative or multiply by a negative. So we would have -9 right here, and it's going to be a closed dot going to the left. And maybe just to reiterate, why is that important? Because when we do these operations, we need to maintain truthness. That is to say, if I were to take a value, let's say a value less, let's say we took -10, and I were to plug it back in here, I should have, you know what, let's change it, make it a whole number. So let's say -12. Let's say we were to take -12, and you were to plug it back into the original, you would end up with a negative times a negative, which would be a +12 divided by 3. And that simplifies to 4. So 4 is greater than or equal to 3, which again is the original. So one thing to keep in mind is whenever you divide or multiply by a negative, you do need to go ahead and change the direction of the inequality so that your solutions, when plugged back in, give you a true statement. At this point, we have most of the basics. I would encourage you to go ahead and maybe pause and try these next 3, but I'll still go ahead and give you the solution just so you can hear the explanation. So pause, give it a try. Let's go through them. In the case of number 6, again, we have to do our order of operations backwards to isolate the x. So I'm going to add 2 to both sides. We get -4 is greater than or equal to 12. Dividing both sides by the -4, we get x is greater than, less than or equal to -3. So if -3 is right here on our number line, our solutions are going to be a closed dot going to the left. Okay, number 7. So we have -12. Let's take that away from both sides. So you get -4. -8 is greater than 4x. And again, just to maybe call it out explicitly, I divided by -12. You don't need to change the inequality there. So I'll go ahead and divide both sides by 4. So we get -2 is less than x. But be careful here, because if this is our first encounter where we're doing an exercise where the x is on the on the right side. -2 is less than x, so that means the values of x that make this true are the ones that are greater. So let's say -1, 0, even 0.5. So just keep in mind that this is equivalent to, so if you wanted to change this, you could change this as x is greater than -2. You can flip that. But that means when we have our -2, it's going to be an open dot because there's no equal to, and we're going to be going to the right this time. So again, be careful. It's only the direction the inequality points whenever the x is on the left side of the inequality statement. All right. In the case of number 8, it gets a little more challenging, but because we just need to collect like terms. I'm going to go ahead and keep my x's positive. That is to say, I'm going to subtract 6x from both sides. So I'm moving the x's over here. So I'm going to move the constants over to the right. So at the same time, I'll subtract 8 from both sides. So this gives us a 3x is less than or equal to -12. Divide by 3. You get x is less than or equal to -4. So if -4 is on our number line, it's going to be a closed dot going to the left. All right. On the next page, we just have a few more examples with other operations that we haven't worked with yet in this lesson. We have before. So I would, of course, give you a moment, try and pause it, or go and pause it and try to work them out. Here's the solutions. Okay, in the case of number 9, I need to first distribute the 3 to get 3x plus 27 is less than or equal to 4x plus 11. So I'm going to subtract 3x from both sides in order to keep the x's positive. At the same time, I'll subtract 11 from both sides. And let's see what that gives us. 27 minus 11 is going to give us 16. And that is less than or equal to 4 minus 3 is just 1x, but you don't need to write the 1. So this, of course, is going to be equivalent to x is greater than or equal to 16. So therefore, 16 is on our number line. It's a closed dot because of an equal, and we go shade to the right. In the case of number 10, we have distribution on both sides. So distribute the 4. So we get 8x plus 4 is less than distributing the 2, 8x minus 6. So what would end up with, in this case, let's see, double checking my math. Good. So you'll see that this is an inconsistent equation because when you subtract 8x from both sides, you get 4 is less than minus 6. So notice right here, this one has no solution. So in the case of number 10, we can, you could put 0, but just keep the number line blank. There's no solution. That is a false statement. And finally, in the case of number 11, we have a compound inequality. So 11 and 12 will illustrate a compound inequality. And the principle is the same. I need to isolate the x. So I'm going to add 4, but I need to add 4 to all parts of the inequality. So adding it to all, the left side, the middle, and the right. So 6 is less than x is less than 10, less than or equal to 10. So 6 is right here on the right, 10 on the left, and is an open dot over the 6, a closed dot over the 10, and we shade in between them. We won't really ever shade, in the case of this course, we won't be shading to the left or the right. That's just outside of the scope of what we know, but you would need to go ahead and essentially use two inequalities to do that. And then in the case of number 12, we just have two operations. We have to subtract 4 from all parts of the inequality. So minus 6 is less than or equal to 2x is less than or equal to 6. And then we divide all parts of the inequality by 2. So minus 3 is less than or equal to x, or 1x is less than or equal to 3. So you have minus 3 on the left, minus positive 3 on the right. Both are closed dots because of the equal to parts, and again, compounds we are shading in the middle. So those are the basics, and in the last part of the lesson, we'll look at some word problems, applications of inequalities. So we have 3 examples. Grandma and Grandpa are celebrating their 75th wedding anniversary by having a party at a local clubhouse. They have budgeted $2,200 for the party. And if the clubhouse charges a flat rate of $200 for the setup and cleanup plus $20 per person, determine the maximum number of guests that can be invited to remain within the budget. So, a couple of things to keep in mind right here is that a flat rate is going to not have a variable next to it. So that's going to just be a flat rate. We're going to need to spend at least $200 just to have the party. And then the per person is going to be some sort of variable. So we'll have 200 plus 20 per person. So we'll just let the per person be our X. And so this is the cost depending on how many, and determine the maximum number of guests. So that is to say, this whole quantity cannot exceed, it's allowed to be equal to the budget, which was $2,200. So there is the setup of this one right here. And then we can go ahead and solve that like we had previously. So subtract 200 from both sides. And you end up with a 20x is less than or equal to 2,000. Divide both sides by 20. So x is less than or equal to, again, you could cancel the zeros, it's going to be 100. So in this case, x is less than or equal to 100. So determine the maximum number of guests that could be invited and remain within budgets. So at most 100 guests can be invited. All right. And all right. In the case of number 14, we have a business. For a business to make a profit, its revenue must be greater than its cost. So again, revenue, is just how much you make. And cost is the expense to actually run the business. So if you start a car wash business with your best friend, where your weekly cost equation is given by this. So maybe just to highlight some things to keep it organized. So here is our cost equation. So that's going to replace this C right here. And your weekly revenue equation is R is equal to 8X. So that'll replace that right there. And again, the revenue must be greater than the cost. So that's the hint right there. And if X is the number of cars washed in a week, how many cars must be washed in a week for this business to make a profit? And again, that is to say this must be true in order for profit to be made. Okay, so like we said before, we have R, which in this case is 8X. That must be greater than the cost, which is 0.50X plus 150. Okay, so again, there's a decimal here, but that's nothing that's going to cause an issue. We just subtract the 0.5 or 0.50x from both sides, so you get 7.5x is greater than 150, and divide both sides by 7.5, and you'd find x is going to be greater than 20. So at least 20 cars need to be washed per week. And if I recall, let me check the solution right here. So at least, so 20 cars or more. So this is not quite true. There's a little typo here. It needs to be more than 20 cars. So this should say more than 20 cars. Because if you wash exactly 20 cars, well, you broke even. You're actually out time. So that's not a good scenario, because you did all that work, but you didn't actually make any money. So just a little typo to correct there. And again, maybe just a step back, the cost, there's some going to be like some supply costs. So that's the flat of 150. And then this right here, if you're just doing with your best friend, is not going to be much cost per car, because that's basically what you're going to be, that may just be like water or something like that. So much smaller compared to maybe the chemicals used to wash. And again, this revenue, this constant in front could change based off of what you decide to charge the customers. And lastly, 18. Eric has grades of a 67 and a 78 on the first two tests. And what must he score on the third test? So this third test is our unknown, to an average of at least 80. So recall that an average, what you need to go ahead and do is add whatever items together. And then you go ahead and you're going to divide that by the number of items. So again, that right there is just your average. So to work with this equation, what we need to do is take the first test, 67, plus the second test, 78, and the third test we don't know yet, and the sum of those divided by 3, because there's 3 tests, must be greater than or equal to 80. And at least is the equal to part. If it said more than, then it would just be greater than 80. So again, 80 is where the average would cut off or be the cut, so that's why we're using equal to. To solve this, we'll multiply both sides by 3. So this will be 67 plus 78 plus x is greater than 240. Again, just multiplying both sides by 3. those threes cancel. We can go ahead and add the 67 and the 78. That'll give us 145 plus x is greater than or equal to 240. And lastly, subtracting 145 from both sides, we find that x, let's just put it down here, x is greater than or equal to a 95. So Eric needs to get at least a 95 on that last test in order to average at least an 80. And just a quick sanity check, if you kind of just feel this one out, the last test clearly needs to be greater than these others so that you can bring those up to an 80. But that is a quick look at linear inequalities and a couple of their applications. We worked on them just in the case of a number line. And again, where we're going to go next is we're going to be working with two variables, x and y. So that would put us in a two-dimensional space. And then we do have analogous examples with shading on a graph instead of a number line. But this is the basics to solving linear inequalities. So good luck and have fun.